rod is defined as essentially a lengthened, elongated charge, right? So first we can do a uniform charge rod, uniformly charged rod. So we can say, let's say the charge of the rod is 10 nanocoulombs, right? So in order to do this with the simulation, you would take each of the 1 nanocoulomb charges and then you would place them in a row, right? Like this. Let's see here. So if I want to put 10, so then I would go like this, and then I would say, okay, go 1, 2, 3. I'll put it equidistant from each other to make the charge density uniform. So 3, 4. Let's do it this way. Let's say 1, 2. Okay, like that. So that's 5. And then this is 6. This is 7. This is 8. This is 9. And then this is 10. So to make it uniform, what I want is the distribution of the charges to be the same. So equidistant from each other. So I don't want more charge on the right versus the center versus the left, right? So now I want to be able to say, okay, this is what the electric field looks like, right? In here, the electric field like goes up straight and goes down straight. And then on the side, it begins to curve like this. And then on the left here, it goes straight like this. And then over here, it goes to the right. Right, so then I want to be able, let's turn off the electric field. Then I want to be able to calculate the electric field, particularly along the straight of the electric field there. You see, so right there it's 275. So right here, the electric field is 760, and then it goes. By that point, it's 125. So then if I go along the middle, okay, so then I see it's about 800, 900. Then it decreases to 223 and so on. So let's derive an equation for the electric field along this and along this line. So particularly those two lines. And then we can find out the electric field at any particular point and see if our answer makes sense. So the total charge of the rod is 10 nanocoulombs, right? And then the dimensions are, I did it so that it's 1 meter. Yeah, it's about 1 meter. So I'll make the origin at the middle of this rod, okay? Then it'll be 0.5 meter that way, 0.5 meter that way. So first we could do it as a general variable, negative L over 2, L over 2, right? So then I could put my XY axis right here. So now if I want to find the electric field here, okay, so what I'm going to do is I'm going to take a certain charge element here, and then I'm going to say the charge of that is dq, and that dq is going to create an electric field at that spot radially away from the dq. This is the calculus approach that we're doing. So we're taking each charge and finding the electrical field of that charge and then integrating them along that rod. So then we take another piece from here, another dq, and then we say this one creates an electrical field away from it, dE, right? So then because the rod is symmetric, so whatever is on the right side of the origin is also on the left side. So the electrical field created by that dq and that dq sort of cancels out here. You see, this one and this one, their x component cancels out. You see, so the x component of this is equal to the x component of that. So those are gone. And then the y components double. So then I'm going to say dE y is going to be 2 of this dE times sine of theta, which is this angle here, theta. So I'm going to define this angle that the dE makes, theta, and by similar triangles, that's also going to be this angle, theta. You see, so this angle, theta, is the same as this angle because the electrical field it creates is radially away from that charge, right? So then I'm going to say 2 dE sine of theta, and then I'm going to use the electrical field created by a point charge is equal to k dq over r squared. So this is the charge of that dq, k dq over the distance from here to here, the distance squared. You see, so what happens is that the contribution to the electrical field here is greatest by the middle charge. The middle charge is the closest to that, right? So it creates the greatest electrical field, right? And plus it's in the y direction. As you start going to sideways, right, the ones that are out here, they create a more angled electric field, you see, like that. So their electrical field is going to cancel more, and plus they're further away. So their electrical field is weird. So visually, it kind of looks like this. If I take the electrical field of this guy and this guy, it looks like it's big. You see? Then as you go to this guy, it's a little bit smaller. Then when you get to the far one, it's like this. It's the smallest. You see? So the furthest ones create the smallest electrical field, and plus they're more in the x direction. So they also cancel a lot. So the contribution to the total electrical field of the whole rod is more due to the middle charges, we can say, because they're closer and plus they add up more. Okay, so this equation already has all of that built into it. You see, so then we're gonna say the distance from here to here is x, and then the distance from here to here we'll call let's call that d. Okay, so then this distance r is going to be what? R squared is going to be x squared plus d squared. You see, so then we say dEy is 2k, and then wherever you have here r squared, we're going to put x squared plus d squared. And then what's sine theta? Sine theta is d over square root of that. I mean, d over r, and then r is square root of that. This is kind of what I was like doing yesterday when I was doing the electrical field along the line y equals -1. So where I was getting sine, and then sine was this over square root. And then when I multiplied them, I get 3/2 power, right? So that occurs a lot in electrical field calculations. You get d over square root of x squared plus d squared. And then when this multiplies with that, you end up getting 3/2 power. So first you get r squared, which is just itself, x squared plus d squared. Then you get sine of theta, which is d over another radical of this, of the x squared plus d squared, right? Because r is going to be square root of x squared plus d squared, right? And then square root times the whole gives you 3/2 power. Okay, so far I have this. dy is 2k. I'm going to bring the d out in front. Then I'm going to say dq over x squared plus d squared to the power 1.5. Okay. Okay, then I need to find a relationship between dq and x. So then I define something called the linear charge density, lambda. This is the linear charge density. And definition of linear charge density is equal to dm over dx. Dq over dx. So this is a tool that we use even in physics 101 when we want to find the center of mass of something. We say linear mass density, and then we define it as dm over dx. So it's a way of describing the distribution of the mass or the distribution of the charge. So it tells you how much charge is included in every dx, in every small increment of the rod, right? So then dq therefore will be equal to lambda dx, right? So then I can replace dq by lambda dx. And then lambda, I'm just going to pull it to the side. Then I'm going to have dx over x squared plus d squared to the 1/2 power. Okay, now I'm ready to integrate this. So I'm first assuming lambda is constant. In other words, a small piece of the rod here has the same charge as the small piece of the rod here. So remember when I was placing the charges in the simulation, I was putting them like equally separated. So that means the lambda is constant. So then I can pull it out of the integral. Then I can integrate this. Since it's a uniform rod, I can integrate it 0 to L over 2. Oh, you know what? I have to integrate it 0 to L over 2 because I've already doubled it. Yeah, I've already doubled it. In other words, I've already accounted for the fact that a piece of the rod here and the piece of the rod here combined, they create an electrical field that is in the y direction, you see, because their x components cancel. So I've already kind of accounted for the left side of the rod by doubling, so that when I integrate, I can't integrate negative L over 2 to L over 2. That would be doubling it too many times. So I have to integrate it from 0 to L over 2, and then the 2 accounts for the left side of the rod. So then integrate that. So that gives me the total electrical field in the y direction. And the electrical field here only is in the y direction. I don't need an x direction. Okay, so then 2kd, and then the lambda, if it's uniform, I can integrate this, right? And then if it's uniform, the lambda comes out of this integral as well. So I get q is equal to lambda integral dx. And then integral of the dx is the total length of the rod. So therefore, for a uniformly charged rod, lambda can be replaced by the charge of the rod divided by the length of the rod. Okay, so Q over L. Okay, then I could put that into the lambda here. Q over L. Okay, now let's integrate this. Dx squared over x plus d squared to the 1/2 power 0 to L over 2. So let's go to so if we're doing a general integral with variables, this one should still be able to do it. 1 divided by x squared plus d squared to the power 1.5. Right? Okay. And then from 0 to L over 2. So 0 to half the length of the rod. Okay, this is the answer. L over, okay, so L over, I'll just write that here, L over d squared, square root of L squared plus 4d squared. So that's just the integral portion. Okay. So then that the integral came out to be L over d squared over square root of L squared plus 4d squared. And then now I'm going to multiply that by the 2kd lambda, and the lambda was the q over the L, right? And then the L cancels the L, and then the d cancels the d. And then the final answer is 2kq over d square root of L squared plus 4d squared. Okay, so that's the general equation for the electric field of a uniformly charged rod along the middle axis, right? Along the middle axis, any distance d away from the rod. Okay, do you remember yesterday's lab towards the middle? It said something like, oh, make a rod and then find the electrical field behavior. And then I told you guys to graph it, make a graph it on Excel. So this is actually that equation, the electrical field behavior at any distance d away, right? So then essentially that's what you're doing on that lab. You're just taking the sensor, putting it at different locations, and then the graph should be something like this, right? But then if you focus on the dots that are near the rod, you should find that the behavior of this function gives approximately 1 over d behavior. In other words, the electrical field drops as 1 over the distance when you're close to the rod. Okay, so what would that mean? Let's say you are 2 centimeters away. Let me show you here. Let's see here. Let's say, so if I'm over here, for example, very close. So what is this? Let's say right at that line. You see, 1021, right? So then what would that be? The distance. Each of these small ones. Let's see, each of these lines. Yeah, each of these lines is 10 centimeters, right? From here to here. And then this is 20, 40, no, 30, 40, 50 centimeters. And that's why 2 of this is a meter. Okay, so if this is this right here, I'm about 10 centimeters away, right? So then if 10 centimeters away, the electric field is, this one is so big, the sensor, that it takes up space. So it's about 11, it's about 1100. I'm just going to write it as 1100. Okay. So then what would it mean for it to be linear? If I go to 2 centimeters away, what should the electrical field be? Right now it's showing 640. So 10 centimeters away, the electrical field is 1100. 20 centimeters away, it's 640. Okay, then if I go to 30 centimeters away, it's 425. 40 is 300. And then 50 is about 225. Okay. So I've got this data. Does that look linear to you? So if it was linear, what should happen? Doubling the distance, right, should decrease the electrical field by half. It's not quite. It's almost, I mean, the half of 1100 would have been 550. So it's not quite linear, but that could also be that my sensor is so large that I'm not exactly sure when I'm 10 centimeters. And plus the placement of my charges maybe is not perfect. You see what I mean? So 30 centimeters, what should that be? That one should be 1/3 of that. 1/3 of 1100. Let's see, 3 times this would be 1200. It looks like the one that's kind of off is the first one. Let me see. 10 centimeters. Maybe that's 10 centimeters, yeah. Oh, jumps a lot. Yeah, I see. This could be 10 centimeters. Let's see, 1270. Oh, that'd be much better. Because you notice how my charges are a little bit below this line. They're not, I didn't center them very well. So that's 10, and then maybe that's 20. Okay, so you kind of get the idea. Is you have to place them really well. And so if I did it that way, okay, now it looks more linear. If you double the distance, it's about half. If you triple the distance, this is about 1/3 of that. If you quadruple the distance, this is should be 1/4 of that. Yeah, it's roughly working out. And if you 5 times the distance, it should be this divided by 5. Okay, kind of. But remember, it's linear for a while. So I don't know how long you can go till, you know, the linearity stops. So also this one should be half of this. So any distance, if you double the distance from 20 to 40, this one is halved. Okay, that's working, you see. Now, what if you go to larger distances? Yesterday in the lab, I said, now it should begin behaving as a 1/distance squared. Okay, because as you start getting farther away from the rod begins to look as if it's a point charge, right? So if I go very far away, so let's see here. So let's say I go 1 meter away. Let's say I go 2 meters away. Okay, am I far enough to be called far? Well, there is no particular point where you could be called far, but yeah, I am quite far. So right now I am 2 meters away. and the electric field is 21.2. Well, there's no distance for me to go. Let's go 2.1, 19.3. Let's say 2.2, 17.8, 2.3. Let's see if I think it's bigger. No, it disappeared. Okay, it disappeared. I would have to lower this. Let's see if I go. I'm going to put it more carefully now. Oops. Squeeze one in there. Okay, so 2 meters would be 1, 2. So you go like that, 2, 2.1, 2.2, 2.3, 2.1. Okay, 2.2. Yeah, 2.2. I'm going to go all the way to 2.5. Then I'm going to go to 2.2. Three. Okay, let's stop there. Let's see here. So when I'm far, this is the behavior I'm getting to. These are the numbers. Does that look linear or square behavior? Okay, a quick one we could do is compare 2 to the 3 meters. Okay, if it was linear, what would this be if the relationship was linear? I didn't quite double the distance, but I increased the distance by 1.5, right? So then if it was linear, what would this have been? If you go from 2 to 3, you're increasing the distance by a factor of 1.5, right? 1.5. So then the electric field would decrease by 1.5 if the behavior was linear, right? So 21.2 divided by 1.5. If this number is roughly around there, then the behavior is still linear. I don't think it is. Oops. Doesn't look linear to me. So 21.2 divided by 1.5. Oh no, not 14. Okay, what if it's a square function? What if it's a 1 over distance squared function? How would I calculate what this should be? Then it's just simply the 1 over the 21.2 over the 1.5 squared. Do you see? If it's a square relationship, in other words, if I increase the distance by 1.5 factor, right, then the electric field drops by 1.5 squared. So I think it's going to actually be closer. Haha. Yes, yes, yes. So already within the dimensions of the screen of the computer, right, I've already gone from a linear to a square. That's pretty fast. And then in the middle, it's probably neither of the two, right? So how could I prove that mathematically with the function that I derived? So I proved it just simply from the simulation, but how would I prove that mathematically? I will take the limit of this function as d goes to 0, okay? In order to find out the behavior of this function, I take the limit as d goes to 0. Now, this isn't quite the limit that you do in calculus where you say, oh, okay, if d is 0, that means this becomes almost 0, so that means it becomes infinity. That's not what I'm talking about. I'm saying assume that this is a small number compared to the length of the rod. So then what's the behavior of this function? Well, when this is a small number compared to the length, you could ignore it and the length dominates, right? So that means the behavior of this function approximates what? 2kq over d times what? If this is being added to that and it's a small number, that means it's just square root of L squared. Okay? So then that's going to be 2kq over dl. So basically, the behavior of the electrical field when I'm near the rod, even though this is the general equation, but we could also approximate this equation by this equation when the d is small. So it's 2 times the k value times the charge over the length of the rod and d. There you go. There you have it. That's the proof of the linear behavior, of the electrical field. Any questions? Any wows? Usually when I do this, students tell me, oh, it's the first time that we've actually seen something like this, like an approximation of this type. Have you ever done that in the calculus? Have you seen that kind of thing? Limit?
Yeah, I remember some of this stuff from Calculus 1.
No?
Wait, can you hear me? Hello?
I think your volume is muted. I'm not sure who's talking, but
Am I muted?
Anthony, I think. No. Some professor, but their volume is pretty low.
Oh,
Whose volume?
probably mine.
Anthony, sorry.
Oh, somebody's trying to talk and I can't hear them? Oh.
Yeah, I don't know. It might. I don't know why my mic's doing this. It's always like low or something.
Oh, it's low. You were talking? I couldn't hear. Oh.
Yeah.
What were you saying? Have you seen that before?
Yeah, I've seen this back in like Calculus 1.
Oh, where they say...
They were explain. It was really earlier on where they were explaining limits.
Yeah. Oh, way at the beginning of calculus?
Yeah.
Oh, nice. That's good.
It was
I
like what,
don't
second
remember.
chapter, I believe.
Oh, yeah? Where
Yeah.
they say, oh, okay, I think I know what you mean. Yeah. Where you're first doing limits and you could ignore something when it's smaller. Yeah, I think I know which ones you mean. Like, do you mean, let's say, limit as x goes to 0, x squared plus 4 over these kinds of things, like x plus 2. Oh, if this is a small number, then you could ignore that and then ignore that. Oh, okay, yeah. It's something like that, right?
Yeah.
4 over 2, and then therefore it's a 2. Yeah, it is the same idea. Yeah, exactly. Yep, it is done in calculus. I don't know why. A lot of people say they haven't seen that before, but you're right. Yeah, that's same idea.
Maybe they forgot, or maybe
Yeah.
like
Well,
some-
maybe they haven't seen it applied to equations such as this, you know, where they've seen it more like this kind of idea.
I see. Also, is my mic better now, or is it still
Oh
low?
yeah, it's better, much better, clear.
Okay.
Yeah.
It was tangled
That's good.
wires. All right.
Oh, okay. Okay, then the other way to go far, we say let's take the limit when the distance is getting big to infinity, and then what does the equation give you? So then now if this is big compared to this, we can eliminate this guy, right? Then we can say 2kq over d, the square root of 4d squared. Now this is actually even more exciting because look at what happens. 2kq over d square root of 4d squared is what? 2d, right? And then the 2 and the 2 cancel, and then you have our famous equation kq over d squared. Oh, that's perfect, because that means when I'm far away from the rod, and even within the limits of the screen, it is kind of matching. I am far from the rod, because as soon as you find out that the square thing is working, that means that's still considered far away from the rod. That means you can simply use the electrical field of a point charge to find the strength. In other words, let's see if this equation will work without necessarily using this longer equation. If I wanted to find 3 meters away for that rod, right? What would I do? This is telling me I can replace that equation with this equation, and it'll approximately give me the same answer. 9 times 10 to the 9th. What was the charge on my rod? I put 10 nanocoulombs, I think. Divided by, if I'm 3 meters away, 3 squared. Well, actually, I could do that without a calculator, because this cancels this. 9 cancels 9. Oh, 10 newtons per coulomb, and it's approximately 10. You see? So for 3 meters, I don't need to apply that equation. But of course, at the, if you're not using the simulation and you're just given a random rod and you're told, find the electrical field at a certain distance, how are you going to know, oh, is that distance far enough to be using this equation? So if you're not sure, you're always a safe bet to use this equation. So if you're going to use this equation, what would you do at that same point? 2, 9 times 10 to the 9th, q, you would put 10 times 10 to the minus 9 over d would be 3, square root of, the length was, what was it? Oh, the whole length of the rod was 1 meter, I think. Yeah, the length of the rod from here to here was 1 meter. Okay, so then I'm going to say square root of 1 squared plus 4 times 3 squared. So the key is that 9 times 4 is 36. You see, when you add 1 to it, it doesn't affect the 36 a lot. You see, that's what's happening here. But this will give me a more exact answer. So 9 times 4 is 36 plus, and if I add 1 to it, and square root it, multiply it by 3, then invert it, and then multiply it by 18 times 10, that's 180. Multiply it by 180. You see, it gives me 9.86. That's actually better. See, that gives me closer to my 9.78. You see? So this always gives you the more accurate answer because it accounts for the length of the rod. But the KQ over R squared tells you, okay, it's approximately equal to the electric field of a point charge. You see, 9.86 is very close to 10. Now, if I go further away, like 4 meters away, 5 meters away, 10 meters away, well, then this and that number will approach each other, and they'll be almost identical. You see? So that means you always can use this, and you can always get a better answer, a more accurate answer with that technique. Any questions? So now we have proven the fact that actually that proves that this equation is correct, because when I found the limit of this equation as d goes to big numbers, I got the equation for the electric field of a point charge. Okay. Now I can use this equation to check the near ones. So what would be the electrical field if I'm 10 centimeters away? Let's say I want to check that one. So then I could just simply use that equation. 2 times 9 times 10 to the 9th. Okay, and times q, which is 10 to the minus 9, over d is 0.1, and then the L is 1 meter. So that gives me an approximation to what the electrical field should be at 0.1 meters. It's approximation. So this one cancels. 18 times 10 is 180 over 0.1 is 1,800. Oh, it doesn't, it's not close. 1270. Wow, didn't come out that close. Hold on, 2 times 9 times 79 times 10 over 0.1 times L. Now, what if I had used this? It should come out close to that. See, if I had used this, what would it give me? 2 times 9 times 10 to the 9th, 10 times 10 to the minus 9, over the distance would be 0.1 square root of 1 squared plus 4 times 0.1 squared. That should give me, if this equation is right, it should give me a more exact version of that equation. Let's see. So let's start from the bottom. 1 plus 4 times 0.1 squared equals square root times 0.1 inverted times 18 times 10. Yep, 1765. So this is an approximation to that. This is the better one, of course. This is the more exact. You see, but the approximation is close. It's not that close, but it is close, you know. So, okay. What was I going to say? But that's still not close to my data here. That means something is wrong with that. Maybe the placement of my sensor. It should be bigger. Okay. Okay, now let's find the... now let me show you what you would do if you didn't want to necessarily derive a general equation and you just wanted the number right from the beginning. So let's say I just wanted to know what the electrical field is 3 meters away, right? 3 meters away, without necessarily deriving the general equation and seeing if the numbers make sense and stuff. So what you would do at this point right here where you had 2kd, right over here, 2kd q over L. Then I integrated here from 0 to L over 2, right? So at this point, I can now put in my numbers. So if I want a numerical answer, so E is going to be 2 times 9 times 10 to the 9th times D. Let's say I want to know the electric field 3 meters away. And then lambda is Q over L. That's going to be 10 times 10 to the minus 9 over L, which is 1. Then I'm going to integrate this from 0 to 1 over 2, which is going to be 0.5 dx over x squared plus 3 squared to the 1/2 power. So that would directly give me a numerical answer without coming up with an equation like this. So sometimes we just want an answer, a numerical answer, without analyzing like that. So that's what you would do. Okay, so let's go. So then you would just go to the integral calculator, scroll up. So then over here, put 3 for the distance. And then over here, put half a meter. There you go, and then press enter. Now it's going to give you a numerical answer. Okay, then once you get that answer for this, 0.0, let me write it on my calculator, 0.018266554. Okay. So once you get that integral answer, then you multiply it by lambda, which is Q over L, right? So L is 1, so it doesn't do anything. And then the 10 to the 9th, that cancels this guy, right? And then the 2 is from this 2, right? So then I'm going to multiply this answer by 10 times 3, so let's say 30. Then multiply it by 9 times 2, which is 18. Okay, 9.86. That was the answer, right? So that was the answer when I did the exact solution. Let's see, was it somewhere down here? Oh, right here. So when I got the general equation and I put the L is 1 and the D is 3, I got 9.86, right? And now I just got 9.86 when I get a numerical answer. So those agree. Perfect. Okay, so now we know how to do a general answer. We know how to find out if the behavior of the electrical field, right? And we know how to get a numerical answer. Now let's find the electrical field along the length of the rod this way, okay?